Hi, this is Francis Massen from the Computerium. As I'm preparing an expose on analog computers, I came on a paper talking about chaotic behavior of a simple electronic circuit. This paper is from 2008, and the circuit is a well-known circuit which behaves as a Duffing-Holmes chaotic oscillator. Here is the circuit that contains only two diodes, an operational amplifier, three resistors or four resistors, an inductor and a capacitor. And the behavior, the chaotic behavior, will be seen in analyzing the voltage of the capacitor and the current going through the inductor. To simulate this behavior, we will draw the circuit in Multisim, also called electronic workbench. Here is this circuit, and the Duffing-Holmes equation, differential equation, can be shown as being equal to the second derivative of parameter x is equal to minus k times the first derivative minus x at the power of 3, and now comes the excitation by a sinus or a cosine signal. The relevant behavior or the parameters describing the behavior is essentially here in this signal generator of a fixed frequency of 1.55 kHz, the amplitude which is here now on 15 millivolt. Here you see the output of a dual channel oscillator operating in XY mode. The X channel is the voltage across the capacitor, and the Y channel is a voltage proportional to the current going through the inductor. And to have a floating input, we use a second amplifier, differential amplifier, for this input. What you are seeing here is the behavior with an amplitude of 50 millivolt. Now I will stop the simulation and let's change this amplitude to 150 millivolt. So here we have it. And we will launch the simulation again. I have to adjust the amplitudes to get a correct picture on the scope. And here you have the start of what will be called later on a strange attractor. Let me just fix this different channel amplitudes to show you. It's not a circle, but it gets to a structure akin to a boomerang. So let's stop the simulation and change the voltage from 150 to 250. And we will launch the simulation again. So this is a better picture showing you the traditional well-known feature of a strange attractor. That means that the oscillating circuit, or that the parameters like voltage here and current here are behaving in a chaotic manner. We will stop the simulation and go slightly up to 283 millivolt. as an amplitude. Let's start again. So the picture doesn't much change. We are in a, let's say, something like a stable chaotic situation. Let's go up by 2 millivolt, just to 285, and launch the simulation again. Now you see the strange attractor feature has changed dramatically, and we have here another strange attractor, a chaotic behavior with the features oscillating heavily between extreme positions, but occupying not all the room but preferential positions, which are the feature of a strange attractor. Let's go on to 290, and we will launch again. So the feature is about the same, and let's look at the signal of the current going through the inductor. So I switch to 0, the first channel, and we go into a YT display, and here you see very well that we have an irregular, let's call it a chaotic behavior of that parameter. So this real simple electronic circuit can be used to show how very small changes of a relevant parameter put a system from a more or less stable behavior into a chaotic behavior, giving rise to the strange attractor. Thank you very much for your attention.